CPU exceptions. CPU exceptions occur in various erroneous situations. For example, when accessing an invalid memory address or when dividing by 0. To react to them, we have to set up an interrupt descriptor table that provides handler functions. At the end of this post, our kernel will be able to catch breakpoint exceptions and to resume normal execution afterwards. This blog is openly developed on GitHub. Right. That paragraph is in every single one. Okay. So, an exception signals that something is wrong with the current instruction. For example, the CPU issues an exception if the current instruction tries to divide by 0. When an exception occurs, the CPU interrupts its current work and immediately calls the specific exception handler function, depending on the exception type. On x86, there are about 20 different CPU exceptions types. I wonder why the about is there. The most important are page fault, that's for illegal memory addresses, invalid opcode, although I don't know how many of those exist given the x86 architecture. General protection fault. This is the exception with the broadest range of causes. It occurs on various kinds of access violations, such as trying to execute a privileged instruction, in user level code, or writing reserved field in the configuration registers. A double fault is when an exception occurs, the CPU tries to call the corresponding handler function. If another exception occurs while calling the exception handler, the CPU raises a double fault exception. This exception also occurs when there's no handler function registered for an exception. And then you have triple fault. If an exception occurs while the CPU tries to call the double fault handler function, it issues a fatal triple fault. We can't catch or handle triple fault. Most processors react by resetting themselves and rebooting the operating system. For a full list of exceptions, check out the OS Dev Wiki. Okay. Interrupt descriptor table. In order to catch and handle exceptions, we have to set up a so-called interrupt descriptor table, IDT. In this table, we could specify a handler function for each CPU exception. The hardware uses this table directly, so we need to follow a predefined format. Each entry must have the following 16-byte structure. We get the lower bits of the pointer to the handler function, a GDT selector for the global descriptor table. There's options. There's another function pointer and another function pointer. And then we have 32 bits of reserved. Okay. So I guess it grew, right? Initially, function pointers were only 16 bits, so it all just fit there. And then when they went to 32-bit, they tacked this on, and then when it went to 64-bit, they tacked that on. And I guess they're reserving this in case it goes to 96 bits. Why wouldn't they just extend it to 128? Okay. The options field has the following format. The interrupt stack table index. Don't switch stacks. Switch the nth stack in the interrupt stack table. Interesting. Some reserve bits. Interrupt gate versus the trap gate. If this bit is 0, interrupts are disabled when its handler is called. Okay. These bits have to be 1. This bit has to be 0. We have the privilege level. Minimal privilege level required for calling its handler. And then 15 is present. Okay. No description on that one. Each exception has a preferred IDT index. For example, the invalid opcode exception has table index 6, and the page fault exception has table index 14. Thus, the hardware can automatically load the corresponding IDT for each exception. The exception table in the OS Dev Wiki shows the IDT indexes of all exceptions in the vector NR column. Vector number? When an exception occurs, the CPU roughly does the following. Push some registers on the stack, including the instruction pointer and R-flagged register. Read the corresponding entry from the IDT. Check if the entry is present. Raise a double fault if not. Disable hardware interrupts if the entry is an interrupt gate. Bit 40 not set. That's this bit 8 here. Load the specified GDT selector into the CS segment and jump to the specified handler function. Don't worry about steps 4 and 5 for now. We will learn all about the global descriptor table and harder interrupts in future posts. Oh, good. Instead of creating our own IDT type, we will use the interrupt descriptor table struct of the x86-64 crate, which looks like this. Let's see if we can, we can pull it up this way, we can take a look at the source. Oh, I didn't build the docs. Maybe I can do that. Cargo doc. Let's get the docs going. And we can take a look at it that way. And we can take a look here in lib.rs on x8664. Whoops. 8664. There it is. And we should be able to pull up the API reference here. And we should be able to interrupt descriptor table. There it is. Show 21 fields. Yeah, okay, so this is this that we're looking at here. All right. The fields have type IDT entry F, which is a struct that represents the field of an IDT entry. The type parameter F defines the expected handler function type. We see that some entries require a handler func. That's the handler func. And some entries require a handler func with error code. There's one. Invalid TSS. A page fault even has its own special type, page fault handler func. That was number 6, right? 1, 2, 3, 4, 5, 6. No? Oh, it's all the way down here. Oh, I must be misremembering the number. Okay. Let's look at the handler func type first. Extern x86 interrupt. Interrupt stack frame. It's a type alias for an extern x86 interrupt function type. The extern keyword defines a function with a foreign calling convention, right? Because we have like extern C in our code, right? For the start function. And is often used to communicate with C code. But what is the x86 interrupt calling convention? Exceptions are quite similar to function calls. The CPU jumps to the first instruction of the called function and executes it. Afterwards, the CPU jumps to the return address and continues execution of the parent function. However, there's a major difference between exceptions and function calls. A function call is invoked voluntarily by a compiler-inserted call instruction, while an exception might occur at any instruction. In order to understand the consequences of this difference, we need to examine function calls in more detail. Calling conventions specify the details of a function call. For example, they specify where function parameters are placed, for example, in registers or on the stack, and how results are returned. On x86-64 Linux, the following rules apply for C functions. First 6 integer arguments are passed in registers, additional arguments are passed on the stack, and the results are returned in RX and RDX. Note that Rust does not follow C ABI. In fact, there isn't a Rust ABI yet. Oh, okay. So these rules apply only to functions declared as extern C function. The calling convention divides the registers in 2 parts, preserved and scratch registers. The values of preserved registers must remain unchanged across function calls, so a called function, the callee, is only allowed to overwrite these registers if it restores their original values before returning. Therefore, these registers are called callee saved. A common pattern is to save these registers to the stack at the function's beginning and restore them just before returning. In contrast, a called function is allowed to overwrite scratch registers without restrictions. If the caller wants to preserve the value of a scratch register across a function call, it needs to back up and restore it before the function call, for example, by pushing it on the stack. So the scratch registers are caller saved. And here's a list of preserved registers. So the callee saves them. The function that gets called has to save these registers. And these are the scratch registers, which means if I call a function, I want to make sure that anything I want to save has to be pushed on the stack before I call and then restored from the stack immediately after the call is done. Okay, the compiler knows these rules, so it generates the code accordingly. For example, most functions begin with a push RBP, which backs up RBP on the stack because it's a callee save register. Okay, preserving all registers. In contrast to function calls, exceptions can occur on any instruction. In most cases, we don't even know at compile time if the generated code will cause an exception. For example, the compiler can't know if an instruction causes a stack overflow or a page fault. Since we don't know when an exception occurs, we can't back up any register before. This means we can't use a calling convention that relies on caller-saved registers for exception handlers. Instead, we need a calling convention means that preserves all registers. Okay. Wording is a little confusing here. The x86 interrupt calling convention is such a calling convention, so it guarantees that all registers are restored to their original values on function return. Note that this does not mean that all registers are saved to the stack at function entry. Instead, the compiler only backs up the registers that are overwritten by the function. This way, very efficient code can be generated for short functions that only use a few registers. On a normal function call, the CPU pushes the return address before jumping to the target function. On function return, the CPU pops the return address and jumps to it. So the stack frame of a normal function call looks like this. So we push 8 bytes of the return address, and then we have the rest of the stack to use for the function. Okay. For exception and interrupt handlers, however, pushing a return address would not suffice, since interrupt handlers often run in a different context. Instead, the CPU performs the following steps when an interrupt occurs. Aligning the stack pointer. Interrupt can occur at any instruction, so the stack pointer can have any value too. However, some CPU instructions require that the stack pointer is aligned on a 16-byte boundary. Switching stacks in some cases. A stack switch occurs when the CPU privilege level changes. For example, when a CPU exception occurs in a user mode program. It also is possible to configure stack switches for specific interrupts using the so-called interrupt stack table. Pushing the old stack pointer. CPU pushes the values of the stack pointer and the stack segment registers at the time when the interrupt occurred, before the realignment. This makes it possible to restore the original stack pointer when they're returning from an interrupt handler. So it does this. Oh, it pushes what the values were before it realigned the stack pointer. Okay, I get it. Pushing and updating the R flags register. Contains various control and status bits. On interrupt entry, the CPU changes some bits and pushes the old value. Maybe it does this in the opposite order. It pushes the old value and then changes some bits. Pushes the interrupt instruction pointer. Before jumping to the interrupt handler function, the CPU pushes the instruction pointer and the code segment. This is comparable to the return address push of a normal function call. Pushing an error code for some exceptions. For some specific exceptions, such as page fault, the CPU pushes an error code which describes the cause of the exception. And then it invokes the interrupt handler. CPU reads the address of the segment descriptor of the interrupt handler function from the corresponding field in the IDT, then invokes this handler by loading the values into the RIP and CS registers. So the interrupt stack frame looks like this. An optional error code, the instruction pointer and code segment, R flags, and a stack pointer. Oh, I see. They're having this grow down. Okay. I'm used to stacks growing up. Yeah, so this is growing down too, so I misread that. In the x86-64 crate, the interrupt stack frame is represented by the interrupt stack frame struct. Let's take a look at that one. Oh, it's got private fields. Which means I gotta drag this over here and look at the source. Oh, it's interrupt stack frame value. Okay. Aha, here we go. There's the instruction pointer, the code segment. That's the CS that they were talking about, right? Code segment. CPU flags, that's the R flags. Then the stack pointer, stack segment. So the only thing that's missing from here is that error code. It is passed to the interrupt handlers as mutable and can be used to retrieve additional information about the exception's cause. The struct contains no error code field since only some few exceptions push an error code. These exceptions use a separate handler func with error code function type, which has an additional error code argument. So we can look at that handler. Handler func with error code has this one. Well, it has interrupt stack frame. Also, that's the same one. Oh, the function itself has the error code. Oh, not the stack frame. I see. Yeah, here it is. It's a U64 off the side there. Okay. Okay, behind the scenes, the x86 interrupt calling convention is a powerful abstraction that hides almost all the messy details of the exception handling process. However, sometimes it's useful to know what's happening behind the curtain. Here's a short overview of the things the x86 interrupt calling convention takes care of. Retrieving the arguments, returning using iretq, handling the error code, changes the stack alignment and needs to be popped off the stack before returning. Okay, and then aligning the stack. There's some instructions that require 16-byte stack alignment. So it handles, this calling convention handles it for us. If you're interested in more details, we also have a series of posts that explains exception handling using naked functions linked at the end of this post. That might be a little too much detail. Now that we've understood the theory, it's time to handle CPU exceptions in our kernel. We'll start by creating a new interrupts module that first creates an int IDT function that creates a new interrupt descriptor table. Okay. Oh, we're going to put it under control of the lib here, pub mod interrupts. And then we'll say edit source interrupts. Use x86 64 structures IDT interrupt descriptor table. There we go. Pub function init IDT. We're just creating one here on the stack and then dropping it. I'm not following. How's that going to work? Yeah, it's just saying we don't have any defined. And there's no reason to be mutable. I'm sure that's going to change, but at some point we have to make this. Okay, we'll figure it out. Now we can add handler functions. We'll start by adding a handler for the breakpoint exception. The breakpoint exception is the perfect exception to test exception handling. Its only purpose is to temporarily pause a program when a breakpoint instruction int13 is executed. The breakpoint exception is commonly used in debuggers. When the user sets a breakpoint, the debugger overwrites the corresponding instruction with the int13 instruction, so that the CPU throws the breakpoint exception when it reaches that line. When the user wants to continue the program, the debugger replaces the int13 instruction with the original instruction again and continues the program. There's a little more details than that, because if you're going to hit that breakpoint again, you want the int13 to be there. So it's a little different, but that's essentially it. For more details, see how debuggers work. Okay. For our use case, we don't need to overwrite any instructions. Instead, we just want to print a message when the breakpoint instruction is executed and then continue the program. So let's create a simple breakpoint handler function and add it to our IDT. Okay, extern x86 97 interrupt function breakpoint handler. And we're going to create a stack frame of interrupt stack frame. It doesn't return anything, and it just says println exception breakpoint. It's hard to type all caps. And then we're going to print out this thing here like this. Stack frame. Right, that's all we need. And oh, we do need a closing quote. Okay, println doesn't exist. Oh, use create println. Interrupt stack frame. Oh, I got to add it here. Right, let's add that. And we still have did I misspell this? INT or RUPT? No, still doesn't like it. Oh yeah, here it is. x86 interrupt ABI is experimental and subject to change. So that's the error. This error occurs because x86 interrupt calling convention is still unstable. To use it anyway, we have to explicitly enable it by adding feature ABI x86 interrupt on the top of our librs. Okay. Has to be up here. Not in the interrupts file, but here. Feature ABI x86 interrupt. Okay. Still not liking it. Oh, because I typoed that. Okay, so now we have 4 warnings. Because we're not using breakpoint handler. Okay, loading the IDT. In order that the CPU uses our new interrupt descriptor table, we need to load it using the lidT instruction. The interrupt descriptor table struct of x86-64 provides a load method function for that. Let's try to use it. Okay, so I guess we're going to go back here. We're going to, up here, we're going to say IDT breakpoint set handler function. Breakpoint handler. And then we're going to say IDT.load. But this is still on the stack. When we try to compile it now, the following error occurs. Oh, it does not live long enough. Okay, so that's Rust telling us that... Yeah, that this thing is going to disappear. So you can load it all you want, but it's going to go away, and you're not going to have an IDT anymore. So load method expects a static self. Oh, really? That is a reference that is valid for the complete runtime of the program. The reason is that the CPU will access this table on every interrupt until we load a different IDT. So using a shorter lifetime than static could lead to use after free bugs. In fact, this is exactly what happens here. Our IDT is created on the stack, so it's only valid inside the init function. Afterwards, the stack memory is reused for other functions, so the CPU would interpret random stack memory as IDT. Luckily, the interrupt descriptor table load method encodes this lifetime requirement in its function definition so that the Rust compiler is able to prevent this possible bug at compile time. In order to fix the problem, we need to store our IDT at a place where it has static lifetime. To achieve this, we could allocate our IDT on the heap using box and then convert it to a static reference, but we're writing an OS kernel and thus don't have a heap yet. As an alternative, we could try to store the IDT as a static. However, there's a problem. Statics are immutable, so we can't modify the breakpoint entry from our init function. We could solve this problem by using a static mute. This variant compiles without errors, but it's far from idiomatic. Static mute S are very prone to data races, so we need an unsafe block on each access. Lazy static. Okay, so yeah, we've done lazy static before. I guess they're trying to reintroduce lazy static. I think this is the third one we're adding to the OS. We already imported lazy static crate when we created an abstraction of VGA text buffer, so we can directly use the lazy static macro to create a static IDT. All right, so that's what we're going to do here. Like that, and then we just macro it. Lazy static ref IDT. And then it's just these 3 lines. And then in init we just say IDT.load. Now where is this being allocated, I guess? I'd like to know. Because if we don't have a heap, this must be allocated in the data segment. And then when we run this, we're just writing into the data segment. Maybe? All right, let's see what happens. We still have an error. Mismatched types. Oh, I just want to return the IDT. Oops, I left the dot on there. Let's try again. There we go. Okay. Note how this solution requires no unsafe blocks. The lazy static macro does use unsafe behind the scenes, but is abstracted away in a safe interface. Okay, so running it. The last step for making exceptions work in our kernel is to call the init IDT function from our main.rs. Instead of calling it directly, we introduce a general init function in our librs. Okay. So this is the testable stuff. I don't know if this belongs here, or if we should put this in a separate test thing. Here's start. So maybe here should be... Oh, this doesn't need to be no mangle. Pub fun init. Interrupts init IDT. And then in start... Oh, now we can update the start function of our main to call init. Don't we need to also end the start for the lib? Maybe not. Okay, well, we'll put it here in this start. We print out hello world, and we call BlogOS init. It compiles. When we run it in QEMU now, we see the following. We do. The CPU successfully invokes our breakpoint handler. Where are we actually invoking the break? Oh, here it is, right here. So we gotta say x86 64 instructions interrupts int 3. Okay. So now if I don't run, say cargo run, it should build it. And we get, it's slightly different, but it's essentially the same thing. The vert adder is slightly different, but it's in code segment 8. We have CPU flags 2. This has 216. The stack pointer is different. That's okay. Oh, and then I didn't print out it did not crash. So let's print that out just to make sure that it did not, in fact, crash. So after test main and just before the loop, we say println it did not crash. Bang. There it is. Okay, it did not crash. Good. Cargo add source lib, not source lib, source interrupts. Not cargo add. Git status. Git add -am interrupt handler for int 3. Okay, very good. The CPU successfully invokes our breakpoint handler, which prints the message and then returns back to the start function where the it did not crash message is printed. We see that the interrupt stack frame tells us the instruction and stack pointers at the time when the exception occurred. I think my audio is a little too high here. There we go. Okay. This information is very useful when debugging unexpected exceptions. Adding a test. Let's create a test that ensures that the above continues to work. First, we update the start function to also call init. The start function in lib.rs. So this calls init here and then test main. Okay. Remember, this start function is used when running cargo test lib. Since Rust tests the lib.rs completely independently of the main rs, we need to call init here to set up the IDT before running the tests. Now we can create a test breakpoint exception test. So we're just going to invoke that instruction. And that's it. Where's the assertion? The test invokes the int3 function to trigger the breakpoint exception by checking that the execution continues. Afterwards, we verify that our breakpoint handler is working correctly. You can try this new test by running cargo tests or cargo test lib. You should see the following output. Okay. And I'm left a dot in there for some reason. Okay. Cargo test lib. There it is. Okay. Too much magic. The x86 interrupt calling convention and the interrupt descriptor table type made the exception handling process relatively straightforward and painless. If this was too much magic for you and you would like to learn all the gory details of exception handling, we've got you covered. Our Handling Exceptions with Naked Function series shows how to handle exceptions without the x86 interrupt calling convention and also creates its own IDT type. Historically, these posts were the main exception handling posts before the x86 interrupt calling convention and the x86-64 crate existed. Note that these posts are based on the first edition of this blog and might be out of date. So that's interesting. So we're actually done with this whole section, and the next one's called double faults. Okay. Let me take a quick peek at this. Oh, I see. So we actually had separate blog posts for how to handle catching exceptions. Yes, this is similar, but we had a lot more work to do in order to handle the IDT. There's an entry. So they basically took the blog post and made a crate out of it. Some bit fiddling that needs to go on. Yeah, so you really learn the guts of it if you do it this way. But if you have the x86 crate, yeah. And this does the load and executes. This actually executes the instruction. Load IDT. Very interesting. And better exception messages. We have assembly here. So we actually had more exception handlers here. There's a lot more work to get this going. So the crate simplifies things drastically. That's why too much magic. Yeah. So we learned how to do it, but we didn't learn the guts of it. We learned using how to use this crate to implement. I mean, if we take a look at it, this is it. This is all we had to do is set up the IDT, call load, and our functions just use this calling convention and figure it all out. The compiler figures it all out for us. Okay. Maybe we can move on to double faults then.